Please take a look at problem 4 in the packet that will deal with particle motion, but interpreting it from a table of values. Take a moment and read the top and take a look at the table of values that we have. In part A, the particle is going to be at rest whenever the velocity is 0. So I want to try to justify that somewhere the velocity is going to be 0. I can use the intermediate value theorem to do this. If you look at, well, there's a couple of ways we could do this actually. We could look at time 2 when the velocity is 3 and time 6 when the velocity is -1. There has to be a time in between 2 and 6 when the velocity is 0. We could also do between 0 and 10. Either of those options will work. I'm going to go with the smallest interval, so I'm going to go with between 2 and 6. I'm going to say, by the intermediate value theorem, remember that the requirement of the intermediate value theorem is our function, in this case velocity, has to be continuous. Well, since we're told it's differentiable, if it's differentiable, that means it must be continuous. So I'm going to say v of t is continuous. Actually, rather, because v of t is continuous. And because the velocity at time 2 is 3, and the velocity at time 6 is -1, the particle must take on all velocities between 3 and -1. Specifically, there's going to be some time when the velocity is 0. Part B, when is the speed of the particle decreasing, or when is the particle slowing down? Well, remember that for that to happen, the velocity and acceleration need to have opposite signs. I only have 4 time values in my table, but that's all I'm going to look for here. At time 0, well, the velocity is positive, acceleration is 0, so that doesn't count. At time 2, I think this looks good. The velocity is positive, but the acceleration is negative. At time 6, they're both negative, so that's not going to work. And at time 10, they're both negative, so that's not going to work. I'm going to say at t equals 2, because the velocity at time 2 and the acceleration at time 2 have opposite signs. Part C, we want to evaluate that definite integral, and we're told to use a left Riemann sum. Well, it always helps me to draw a little graph, so I'm going to go do that. Let's see. I've got time 0, time 2, time 6, and time 10. I'm dealing with velocities here, so 5, a velocity of 3, velocity of -1, and a velocity of -8. And I'm using a left endpoint Riemann sum. Let me find a different color for this. So it looks like I'm going to have rectangles like this, and then that, and then that. That's perfectly fine that you have a rectangle below the x-axis. The integral from 0 to 10 of v of t dt is going to be approximately, well, the base of my first rectangle is 2, and the height, well, I'm just going to say v of 0 for right now. The second rectangle has a base of 4 and a height of v of 2, and the third rectangle has a base of 4 and a height of v of 6. This gives me 2 times 5 plus 4 times 3 plus 4 times -1. That's 10 plus 12 minus 4, 22 minus 4, that's 18. I integrated the I didn't integrate the absolute value of velocity, I just integrated velocity, That means this value tells me the displacement of the particle, the net change in position of the particle between time 0 and time 10. That's the displacement, or the net change in position over the time interval between 0 and 10. Two more parts. Well, now we're asked to approximate that integral. Similar idea from part C, but now we're doing a trapezoid sum, and we're doing the absolute value of velocity. Sorry, you can't see that. Ah, you can. And we're doing the absolute value of velocity, so we're going to find the total distance here. You can draw this out if you want. I think I'm just going to start doing my calculations, actually. Between 0 and 10 to integrate the absolute value of velocity dt. Well, the first region will have a base of 2, and the trapezoid part means I need to do the absolute value of the velocity at time 0 plus the absolute value of the velocity at time 2, and find the average of those. And then the next trapezoid will have a base of 2, and the height's going to be the average of the absolute value of the velocity at time 2 plus the absolute value of the velocity at time 6. And the last region has a base of 4, and the heights will be, well, I need to do the average of the height, the average of the speed, the absolute value of velocity at time 6, and the absolute value of velocity at time 10. It's probably more complicated to write out than I needed it to be. I'm just going to go and plug in the numbers now. 5 plus 3 divided by 2 plus 4 times 3 plus 1, because remember we're taking the absolute value of velocity divided by 2, plus 4 times 1 plus 8 divided by 2. 2 times 8 halves is 2 times 4. 4 times 4 halves is 2. 4 times 9 halves. Okay, so 8 plus 8 plus 2 times 9, so that's 18, 26, 34. Again, what that gives us is the total distance traveled. One more. Part E. We're asked to determine the value of that integral. Well, I have acceleration values in my table, but we're not told if we should use a left or right or midpoint or trapezoid sum here, and actually we're also not told to approximate this thing. We're told to find the actual value of that. Well, I can actually use the first fundamental theorem of calculus to do this. We're integrating the acceleration from 0 to 10. By the first fundamental theorem of calculus, the antiderivative of acceleration should be velocity. So I'm just going to get velocity evaluated from 0 up to 10. V at time 10 minus v at time 0. I have those velocities in my table, right over there and over there. So I'm going to do negative 8 minus 5. I'm going to get negative 13. Actually, they gave you more information in this problem than we needed. We didn't need anything about that acceleration line that was given to us.